spectrum, UVC at 254 nanometers is the optimal peak wavelength that kills viruses. I'm sorry, that inactivates viruses. We must remember that viruses are not alive. They are simply part of a coating that goes in and replicates itself. So in this true sense, it only can be inactivated. It does kill bacteria, UVC, mold and fungi for short exposure. It's an old technology. It's been around for quite some time, as I mentioned before. And there are some exposure risks known, both skin and eye irritation. It is not deadly, nor is it cancerous. UVB, again, this is non-visible and it activates some viruses and bacteria. This is in the 280 to 315 nanometer range. Limited effectivity for viruses and mold, moderate exposure times to produce those effects. It's an older technology, including sunlight, and does have exposure risks, including as a skin carcinogen, many of you are aware of, and UVA actually has the exact same issues of at 315 to 400 nanometers. Again, these are the non-visible wavelengths, so we don't see these, but they have a huge impact on us. And clearly the overexposure for skin burns and causing skin cancer are the risks associated with being exposed to these wavelengths. And then there's something called near UV. So this is actually into the visible range. It does not inactivate viruses, but it has been shown to reduce bacteria, an unknown effect on mold and fungi at this point. It requires a longer exposure, but it turns out that humans can actually be exposed to this wavelength and without any detrimental effects on them. But this is clearly not lighting. Even though I'm a lighting designer and looking at this, this is an aspect of the electromagnetic spectrum that is being utilized. Now, it has a lot of things in common with lighting, but clearly it's not used for visibility. It's only used to irradiate the air and surfaces in order to inactivate viruses or kill mold and fungi and other pathogens. It can be harmful for the eyes and skin when they're exposed too long. It's not measured in the same way, nor does it use the same terminology to define its measurements and its performance. It uses similar lamp technology, but it's more specialized. It's older technology. It's more effective by far when it's integrated with HVAC systems. I would say that GUV is the most integrated solution for utilizing electromagnetic energy. You have to use it with HVAC. Its relationship to air is critical, and absolutely controls are needed for different purposes than what you would utilize lighting controls.
So I can jump in here real quick and talk about some of the terminology that you'll hear. GUV being germicidal ultraviolet, also known as UVGI, which is ultraviolet germicidal irradiation. When we talk about the dose, that's really the irradiance over a period of time. The fluence or fluence rate is the radiant energy measured through a sphere, since UVC projects outward in all directions from the source. The kill rate is simply the effectiveness of deactivating the microbial population, and UV irradiance being the real power of the electromagnetic radiation on a surface. And that's typically measured in microwatts per square centimeter.
Another way that we look at disinfection is really looking at the log reduction of disinfection. And so that's one way of looking at the effectiveness. So when we look at log 1, we're looking at a 90% ability to kill viruses and microbes. At log 2, we're at 99%. And typically a lot of school facilities, depending on which space you are in, can be about log 2. Log 3 is 99.9. Now we're getting to kind of hospital range. 99.99, we're getting definitely to surgical suites and operating rooms. So, and further on, you're getting to laboratory spaces as you get into the deeper logarithmics. So that's really how the infection control reductions are measured, through log reductions. Different UVC dosages rates are actually based upon virus and bacteria. So the dosages can kill at a certain rate, or UVC can kill at a certain rate depending on the type of pathogen that's actually it's killing. And here's a chart actually showing how effective UVC is in killing many of the pathogens that exist. And it talks about a 3-log reduction in kill rate as well. So this is really a helpful chart. What's not included on this chart, though, is COVID-19. But there is an absolutely, they've been studying, they understand the interaction between UVC and dosage for killing COVID-19 or deactivating COVID-19. So I'm going to talk about the lamp technologies that emit UV ultraviolet radiation. Pulse xenon is a very common source, and it's actually a full range UV source, and actually goes even into the visible range. So it provides UVA, B, and C ranges, and it gives a pulse. So it both lasts a long time as a source because it's being pulsed, and it can be very powerful. You should not be in a space where this is going off, though, and it can absolutely irritate you and cause some problems. So it's critical that you have good controls when utilizing pulse xenon lamps. UVC lamps, such as are typically, if you can consider them, they're really fluorescent tubes that do not have phosphors. So they're vaporized mercury vapor. And so they produce a glow that's emitting UV and UVC. So you could actually get it to emit the exact 254 nanometer wavelength that can effectively kill and disable viruses. Medium pressure mercury lamps are also effective. They're at the 250 nanometer range. Then there's exciting new technologies such as the excimer lamps. It's a krypton chlorine excimer lamp that has a peak wavelength of 222 nanometers. Microplasma emitters, yes, plasma like your TV set, but they've made them very small that also can be tuned to 222 nanometers. So there are some newer technologies in how to go after UV and create or reproduce UV at the right spectrum. And of course, LEDs. Solid state technology is rapidly evolving to take on and to emit UV radiation. It is a complicated change and that the solid state lighting industry is dealing with in order to do this, simply because UV will damage most of the materials used to locate the LED. So they have to come up with different materials in order to emit the UV radiation. But because there's so much money and so much interest in utilizing LEDs and the other benefits that LEDs provide, smallness in size, efficiencies, and long lasting. And one of the things that I think is also great for HVAC, they love the cold. They thrive in cold. That the LED market, and I'm going to show, will actually start increasing fairly rapidly and be developing viable and much more efficient LEDs for UVC. There are UVC LEDs on the market right now, but their efficiency is incredibly low. Well, that will change. At the same time, UV lamp fixtures and device regulations are also occurring. And so this is a modifying, changing world where people are developing standards to manage this technology. I want to say that the image that I'm showing here is actually not something that I condone, nor do I think it's a viable solution, but it's these gateway UV lamp images that people are touting as being effective in deactivating viruses. There are no studies showing that this is effective. First, I want to talk about ANSI ASHRAE standard 185.2, method of testing UV lamps in HVAC systems. And then there's also the EPA, that this is really interesting. For UV fixtures, they are actually approved through the EPA as a pesticide fixture. So they're a pesticide device, and that's how they're sold, and those are the claims. So that's when you see a manufacturer come to your office and talk about UV, the standards that they're using are some of the EPA pesticide standards for fixtures. UL has stepped up and has developed a standard, UL 8802. It's an investigation, so they haven't created a full standard yet, but it's what they call an investigation for germicidal systems. It's for UV emitters, for switches and sensors, and for the complete system, both UV within HVAC systems and outside of HVAC systems. What's nice about having these standards is suddenly, as litigious as our society is, we suddenly have things that we could point to. So we could look to these standards. We could ask manufacturers, do you have UL 88, do you meet UL 8802? Do you have that stamp? Can you meet those standards? And so suddenly we have a threshold that they have to meet in order to be a viable product. There are some absolute dangers in utilizing UVC, and that's at the 254 nanometer range, 280 to 315 range. There are issues regarding overexposure that can be an irritant to the skin, can absolutely cause things like blindness, welder's flash, photoconjunctivitis, things like that can happen for people who are overexposed. Anyone who's done any welding has probably dealt with this on their skin, where the arc welders will actually leave an irritation if you're exposed to it for too long. That's why you cover up in these types of situations. So having occupancy sensors is critical so that you do not expose not only people, but children to the harm that these things can do for a long period of time. They will not kill you, nor will they cause cancer. In China recently, there was a non-functioning OX sensor that did expose children to UVC, and they were miserable, and they had to have treatment. So it is dangerous, but it's not deadly. There's also the issue of material degradation, and that's because UV can degrade certain materials such as nylons and certain plastics and polymers. So it's important that you check with the manufacturer of your furnishings and your finishes and making sure that they're compatible before installing room-based UV systems, especially for ceiling panels. So now we're going to jump in. Okay, go ahead, Ed.
Oh yeah, so yeah, I'm going to jump into some of the applications of this technology. So as an MEP engineer, I'm really responsible for specifying and applying products and technology that meet our clients' needs, and there's certainly a need for increasing indoor air quality and addressing this virus situation. So UVC can be applied in a number of ways in our buildings. Two main categories we like to look at: UVGI integrated into HVAC systems, and then also room-based UVGI systems. So we will go over a number of different applications of this technology. So the first one is airstream disinfection, which involves mounting UVC lamps inside the ducts or air handlers in your building. This distributes the UVC in all directions, so any air flowing through within line of sight is affected. So the key for us when we design these things is considering dose and duration. So the velocity of the air going through the air handler or duct is a main consideration. You want an absolute minimum of about 1/4 second exposure time, but ideally a full 1 second is better. So again, the air velocity, if you're moving that air relatively quickly through that duct or air handler, you'll need a longer section of duct for that treatment. So the intensity of the lamp is also a major factor that goes into the overall dose. Within an air handling unit, compared to a duct, ducts are typically designed with higher duct velocities, I don't know, 1,000, 1,400 feet per minute max, depending on the location. So with that higher velocity, you're going to need the longer length. In an air handling unit, the velocity is typically around 500 feet per minute. So an 8-foot section gives you a 1 second exposure time. And so it's really a nice application to locate UVC lamps within air handling units. So the next one we'll look at is HVAC coil and surface cleaning application. Wet conditions on cooling coils and drain pans, unfortunately, can promote the growth of biological contaminants. So a common application is to locate these lamps downstream of cooling coils where it can continuously treat both of these surfaces. These are typically lower irradiance, lower wattage lamps. But we often get the question, can I, raise the wattage and kind of kill two birds with one stone and get the surface cleaning aspect and the disinfection aspect? And the answer is yes. You can use more lamps, like 2 to 3 times the lamps, and a higher intensity. And in a 2-foot section downstream of a cooling coil, you can actually achieve, well into the 90s, 99% kill rate. The other major benefits of mounting UVC lamps in this orientation is it keeps your coils clean. So it reduces the costly effort of coil cleaning and reduces using those chemicals that lead to poor air quality, groundwater contamination. It also increases or decreases the fan energy required to push the air through the coil and increases the coil heat transfer performance. Actually, a study done in Florida after they installed this system, it cleaned the coils so well that the air pressure drop decreased by over 20%, increased heat transfer by 15%. And the energy consumption of these lamps is minimal compared to the cost of pushing air through like a HEPA filter, and also minimal compared to the reduced efficiency and increased maintenance. And if you add in healthcare costs, then these things really look attractive, economically attractive. So the GSA, the federal agency that maintains all of our federal buildings, actually mandates these in all of their air handling units. So the next application is upper air in occupied spaces. So an upper air fixture targets the upper zone, the unoccupied zone. So it creates a UV field that's generally parallel with the ceiling above occupants' heads. These can be mounted on the ceiling or on the wall to create that controlled UVC field. So you want to consider the room configuration and type of fixture, locations, and also a big impact is room air currents. You want to make sure that there are no real stagnant spots in the occupied zone, because you're really relying on the air to be circulated through the UVC field to be effective. It's worth noting testing should be done in the commissioning process to ensure, with meters that eye level exposure limits are not exceeded. You can put warning signs on the wall as well if suggested. And the economics really favor the in-duct approach, but we're oftentimes dealing with, existing school buildings that may or may not have full ducted HVAC systems. So this technology can be viable for those situations.
And if I could add, this is the type of application that many lighting manufacturers are looking at applying. So if you have a direct, indirect fixture, it's possible that you could integrate upper air UVGI type of systems into those systems. So I would say in the next 2 years, and especially with the advent of LEDs coming in, we may start seeing more and more of this integrated into lighting fixtures. If, you know, it's not that lighting can't do everything now, sound and everything, acoustics, but we'll be adding this to the lighting plate to handle those spaces.
So the next one that kind of bridges the gap between HVAC and in-room is the upper air type that is fan assisted. So these come in different flavors, if you will. There is a ceiling recessed version. So that light that you see on the upper right has a fan in it and a UV lamp, and it continuously circulates air. So having that fan assist obviously makes sure that the air throughout the room is getting properly circulated through that UVC field for treatment. So the other nice option, this is a relatively new product from a big fan manufacturer, is
right?
But you said it, yep, is UV integrated into the ceiling fan. So like I said, the effectiveness is really a function of those air changes. So when you integrate this into a ceiling fan, it draws all that air from down below and creates that motion that draws the air through the UVC field to be as effective as possible. And so these fan assisted versions are anywhere from $1,400 to about $2,000 per unit.
Now we will look at direct air and surface and occupied spaces. These can be located both in the ceiling, they can be recessed into the ceiling. They operate, some of them actually, there's a new product out by a manufacturer that actually can operate below the threshold of skin and eye damage irritation. So it can provide UVC continuously in an occupied space, utilizing LEDs without irritating eyes and skin for the occupants below. So that's an extraordinary effort to do something like that. So we talked about the evolution of these products. They're coming on strong, and this is one idea that looks like it's somewhat viable for doing that. There's also the far UVC 222 nanometer. I mentioned that before, being that it's a wavelength that cannot penetrate the dead skin cells, upper layer of our skin, so it doesn't irritate our skin or our eyes. And so this also can be integrated into ceiling panels and wall panels that can actually irradiate the room while the room is occupied. Again, these are line of sight only. So if there's a shadow or anything like that, it will not hit those surfaces in the shadow zone. So you're both irradiating air, which we know that the COVID-19 exists in air droplets for quite some time. So that's the benefit of that, but you're also irradiating surfaces as well. Then you have UVA and near UV applications, direct air and surface. So these are where you're looking at kind of, again, continuous decontamination. These are in the range of 365 nanometer to 405 nanometers. They're only used to kill bacteria and maybe some mold and fungi. These are already used in a lot of hospitals because of MRSA and Legionnaires and other type of pathogens that are quite large, and this spectrum of the UV actually can kill it effectively. So it's demonstrated to be non-harmful for occupants occupying the space, and can be incorporated into existing light fixtures. So you get both the visible lighting, but you also get the benefit of the UV lighting as well. Again, it does not kill viruses though, and this is really important. So only when you get to a UVC do you start killing or deactivating viruses at that level. You cannot do it in UVA or B. And then we look at UVC in unoccupied spaces. So where we're applying a strong dose of UVC for spaces that during unoccupied times at night, where you want to deactivate those spaces of viruses in the air and on the surfaces below, you can put in both ceiling mounted panels, wall mounted panels that can go on for a certain dosage, certain time. It doesn't take a lot of time in order to get a 99.9% deactivation rate. So you could be very effective again. Again, it's line of sight, so anything in the shadow on that surface will not be deactivated, but anything in the air that is being irradiated will absolutely be deactivated. There are certain spaces that we think in schools that could actually be really quite effectively use this type of solution. There's also, and many of you may have seen this in some of the recent literature and articles about UV, direct air and service for unoccupied sites, where they use these mobile devices that they wheel out. They've been using them in subway cars in New York. When they're offline, they wheel these things through, turn them on, get out of the way, and basically they irradiate the entire subway car as much as they can see. They move it to different parts of the car so they can cover the areas that are shadowed. It's very effective. They cost a lot of money, but they are incredibly effective. You could also use them in buildings. So a lot of resorts I know in Hawaii are actually utilizing them and having them go from room to room as a robot. So it's like a Roomba with UV. That's pretty cool. And so these can be very effective. They can be programmed to go off if they notice any movement, if anybody's in that space, so that people are not getting the irritant of the eyes and the skin. They're not being exposed by this UVC. So now we're going to look at some application studies. These are studies that we actually had commissioned, or two of them are what we had commissioned, to look at actual classroom and cafeteria spaces, and then we're going to talk about nurses' offices. And before we do this, Ed, you want to talk a little bit about this?
Sure. So in terms of modeling the infection risk, oftentimes we look at, well, back in 1978, this equation called the Wells-Riley equation, it was derived to predict infection risk, originally used to model the measles outbreak in schools, but it can be quite effective for a variety of pathogens. So it basically factors in the number of sick individuals in a space and the exposure time. And you can, and it looks at, with more air changes of clean air, the exposure time is reduced, and likewise the infection risk is reduced. So this is the Wells-Riley equation has been used for decades to help us model the infection risk. It's not, you know, it's not a super detailed model. It's a little bit of a you know, generality, but it's you know, a good tool that we have in our tool chest.
And UVGI effectiveness is also compared to the equivalent air changes per hour. So if you apply UVGI, especially in upper room, you can actually have the equivalent increase in air exchanges, can be up to 10 to 20 air exchanges that actually can be increased within that space. So in many ways, it's making that air healthier in those spaces by utilizing, I think, a low energy solution. So we're first going to look at a classroom. This is actually from a Yale study, but they look at all the different safety guidelines with COVID-19. And so, of course, they look at the obvious ones: hand hygiene and mask and physical distancing and cleaning. They do not mention UVGI. And so, in many ways, some of these solutions are very effective. Natural ventilation becomes a little bit more problematic. And Ed probably would comment on this: is if it's cold, like it is today here in the Northeast, opening up windows is not a viable solution. So having upper air solutions could actually be helpful. So we modeled an upper air room, UVGI, in a space, very simple classroom space, and located two of the units in here. And so I'm just going to show you some of the readings that we got. But fundamentally, we were able to get 30 microwatts per centimeter squared in the darker red, and to the yellow at the edges, up to 10 microwatts per unit per centimeter squared. So we are actually getting a fairly healthy dose of effluence rate within that space by utilizing simply two upper air UVGI units within that space, to a logarithmic of factor of 2 to 3, so 99.9% deactivation of a virus. The units themselves, and here's some more readings, are looking at how much time it would take and how much equivalent air exchanges they are by utilizing these units. So if you look at log 1, 46 minutes, log 2, a little longer, and so on. So getting to a log 3, 99.9, it takes longer time, and it also tells you the equivalent microwatts per meter squared and watts per meter squared that you actually need for the fluence rate in order to achieve that degree, logarithmic degree of deactivation for infection. Anything to add in?
Nope, you covered this one well.
Okay.
So we also looked at an example of applying the fan-assisted upper air technology to a cafeteria. So, you know, obviously larger square footage than a classroom. The fixed upper air fixtures may not be practical for such a large volume of space. So we looked at introducing fan-assisted or ceiling fans. So we had this manufacturer run some modeling, and they can actually, they came out with a layout of 8 ceiling fans for this particular space. This 5,000 square foot example cafeteria. And they actually used CFD modeling to predict the airflow patterns and air circulation within the space. So with those results of the air change modeling, they used the Wells-Riley equation that I mentioned earlier to calculate the infection risk reduction of adding this technology. So again, the Wells-Riley equation factors in the number of sick individuals and the exposure time, and with those, you know, circulation of cleaned air, the exposure time decreases, and therefore the infection risk decreases. So with this example, they were able to show an 82% risk reduction. Basically went from 11% infection risk baseline to 2%. And that was for coronavirus. For influenza A, they had a 50% risk reduction, and this tuberculosis, 88% risk reduction. So it is dependent on strain. So when you're considering this technology, again, you know, it's really dependent on the specific space and the layouts, the volume, ceiling heights, and you know, aesthetics as well. If you want to do something that's you know, more you know, recessed, or you're okay with having exposed ceiling fans, you know, this is just one of the options that you can look at.
And if I could add that they actually are utilizing UVGI LEDs. So this is one of the earlier applications I've seen actually of effectively utilizing LEDs. The LEDs right now are not that efficient, but they, as you can see from the report, actually were very effective in disinfecting that space. Another space that I think is a key candidate within a school that can actually utilize UVGI disinfection are the nurses' offices. And on top of the nurses' offices, we also have isolation spaces that are being recommended so that you can take infected students and or personnel and get them out of the general population and isolate them. Clearly the HVAC systems and the air has to be isolated, so it will not go into the general space of the building. So these spaces are really isolated. They're like laboratories in a sense, but UVGI, direct UVGI could be effective when they're not occupied. So when everyone's gone, you could cleanse the entire space with a robust direct UVGI system utilizing UVC. You could also do it during occupied times with a continuous either 222 nanometer FAR UVC or an effective 254 nanometer that does not reach the threshold of being an eye or skin irritant. So nurses' offices are incredibly critical, both for evaluating students, administering vaccines. They're incredibly important, and these spaces need to be cleaned more often, and they're a high touch area, a place where infections can show up, will be concentrated in these areas. So if we were looking for a good space for buildings, we could focus here and be very effective. So we're again looking at isolated HVAC air. Direct UVC could be used in unoccupied times, and far UVC as well during occupied times. So this brings us to really our final slide, really looking at all the considerations. UVGI integration has to happen with HVAC systems, either in room or in duct. HVAC integration is critical for the success of integrating the germicidal UV. You need to understand the target level of the pathogen. You need to understand what you're trying to reduce and how you want to reduce it. There are ways that you can utilize UVA and B just to kind of get rid of bacterial and mold, but that may not be effective for viruses, and so that may take a different approach. Multi-layered disinfection strategies are key. UV is not going to get rid of wiping down spaces and all the other techniques, including PPE and distancing, and all the other techniques absolutely need to be applied, but it can be an absolutely helpful tool for disinfecting these spaces and reducing the risk of infection in these spaces. And we all know that kids can have a lot of germs, can carry a lot of germs. And that's actually sometimes a good thing, in the sense that some kids, it builds up their immune system when they're amongst each other. But if we could clean the space more and more, I think it could be helpful for these kids and reduce the risk to the adults as well. Determine the cost effectiveness and the risk effectiveness. How much risk do you want to take and reduce as far as infection rates for these UVGI solutions? And it may be a good solution for, as I mentioned, for colder climates where you cannot have open ventilation. UVGI may be a good solution for that. So by improving the air exchanges within that space, a recent study saying that you actually need about 6 air exchanges per hour within a space in order for it to be considered a healthy space. And it has incredible improvements in student performance, alertness, behavioral issues. Air becomes very critical. So if the UVGI can assist in that and provide some infection reduction, it's a very much a positive thing. So I think we have some time for questions. Tina?
It looks like we have a few questions in the chat box. One was on, the last one I saw come through was on reflective, if reflective UVC is effective, and the answer is definitely yes. And I apologize, I should have mentioned that actually during my slide on airstream disinfection. When you apply these lamps inside ducts or air handling units, you should always have a reflective material. Aluminum is excellent. Whether you construct the duct itself out of aluminum, that particular section of it, or you apply a reflective material, aluminum foil really, to the inside. Oftentimes the lamps are mounted to a reflective shroud, and that can go a long way in increasing the effectiveness. It's really actually a kind of a very cost-effective way of increasing the effectiveness of that lamp.
We have a second question regarding whether after COVID and the vaccine renders COVID less of a societal concern, do you think such fixtures will be provided with an eye of addressing future pandemics? Absolutely. Yeah, this was not the big one, believe it or not. They were anticipating a much more deadlier, higher infection rate pandemic, but this has been so deadly and so destructive but hopefully it prepared us so that we can prepare our buildings to be more resilient. So when pandemics show up, we can handle them. We could keep spaces open longer and reduce the infection rate. So this is a tool. This is a tool I think that'll be around for quite some time. And I think it'll become more refined. And as LEDs become utilized more and more, they're going to be able to provide good, robust UVGI within these spaces, integrated seamlessly into these fixtures so that you won't even know that it's happening.
So
Yeah,
there's
you want to take
more
the
comments in the chat if you wanted to address. There's one that asks about other HVAC technologies that might work as well or better at disinfecting air regardless of lighting.
Sure, we always, it should be, like Ed mentioned, UVC is really a complementary technology to, a host of other things like, your basic particulate filtration, which, obviously at different levels of filtration. There's ionization technology, which is an interesting one, less of scientifically proven technology, but it looks like it has merit. And there are, other, like increasing humidity in a space is actually shown. It's, a basic design criteria for healthcare facilities, because it's shown that at lower or a minimum humidity threshold reduces or improves patient outcomes. So there's a target humidity range. So yeah, this is really a complementary technology, and the induct approach, as I mentioned earlier, it should be combined with a degree of particulate filtration. But when you look at UV or increasing your MERV 8 or 13 filter to a full HEPA filter and the associated air pressure drop with that, you can get just as much effectiveness in terms of cleaning the air with a UVC lamp, and actually use less energy doing so. So hopefully that helps answer that question.
I want to go back to the previous question regarding reflectance. And I'm not sure if you were mentioning also space reflectance, but it is critical in upper air applications that the ceiling reflectance has to be reduced. Unlike when we have lighting where we want higher reflectivity within the ceiling, for UVGI, we do not want that irradiation to reflect back into the occupants during the occupied times. So absolutely, it's critical that you coordinate your ceiling reflectance with that solution and aim for a lower reflectance for the ceiling. There's a thoughts on discussing independent testing of fixtures themselves and efficacy claims from Lindsay Dahlman. Be careful what you ask for. I would not be surprised to see a major organization taking on GUV fixtures and certifying them and sanctioning them and creating a qualified products list for these type of things. It may reduce the number of unsubstantiated claims that are happening with a lot of fixtures right now. And so what we say, it will calm the wild west of products that are out there that are doing from wands to everything else. But it also means that these manufacturers will have to, pay some money to get these testing done. But once they're tested and certified, then absolutely the public should have confidence, and designers and specifiers and engineers should have confidence that these systems will work as intended. That's all the questions I have.
So I have one last question before we end.
Yeah.
Typically in our schools, we tend to specify rooftop units that don't recirculate the air. So if we were specifying one of those, would it still be prudent to put the UV light in the ducts?
So that, yeah, like a DOAS system or a dedicated outside air system. So
Right.
if you're bringing in 100% outside air, which I agree is a common approach, you know, the real benefit of UV in the induct approach is to you know, mitigate those the viruses, bacteria that come in through or are recirculated from the space. Now UV is an excellent application in a DOAS system for coil cleaning, because you know, all the stuff that comes in from outside, you know, that, like back to that Florida example, you know, you can grow some nasty biofilms on the cooling coils of a DOAS unit, and if you apply the UV technology downstream of the cooling coil, it'll keep that coil very clean. So you don't have to do that you know, costly coil maintenance with the chemicals, and increases airflow and a whole host of benefits in addition to air quality improvements. So yes, you can definitely see a benefit using UV for a 100% outside air system.
If I may mention that some utilities are looking at providing rebates for coil cleaning UVGI systems, and I think even maybe induct as well. So, so there's something you need to check with your utility and see if they have rebates regarding that. But that's actually because of the efficiency gains that you get with these systems. Utilities are looking at this as providing providing rebates and helping customers get this type of system in their buildings.
There's a question about unit ventilators that came through, and so the traditional, you know, quote, old-fashioned unit ventilators, unfortunately, are not a great application for to insert UV or mount UV in those devices. A, because they're so compact, there's not a lot of room for a UV fixture in them, and they also would have line of sight issues with the grills on top and on the bottom or on the sides. So, you know, I saw a product, I've never specified it, to be honest, that is a unit vent with UV integrated. I don't have a lot of information on whether that, I haven't seen them, frankly, installed. I think you would want to look at an upper air solution, possibly a fan assisted solution, if you're looking to integrate UV into the classroom.
I think we have one final question, and we're regarding estimate of labor costs associated with installation of various applications. I do not have any numbers regarding that. I know it changes depending on your region, but I would, depends on how complex the systems are. Clearly an upper air system, the labor costs are fairly minimal because you're only providing power on the wall or maybe in the ceiling, so that's fairly minimal. Duct, there are some kits where you could do induct type of retrofitting. So I think it varies. It varies under the approach and the conditions that you're placing the system.
There was a question on ionizers, and that's, you know, a good you know, complementary technology that you know, ionizers or bipolar ionization is an interesting one because it's not there aren't the same sort of testing standards, so it's a little bit wild west with that technology. We've seen some promising looking studies where they take a test chamber and they pump it full of ions, like 40,000 per cubic centimeter, and they do show a reduction or a reduction in the viral load on a petri dish compared to a sample. So there's appears to be some merit to ionization technology. And we do see them applied, and those actually can be installed in a unit ventilator system. So yeah, just that's almost another hour presentation just on that technology alone too.
Looks like that's it for our questions. I want to thank both of you for presenting for all of us tonight. It's very interesting technology. I'm hoping we never have to talk about COVID again after this year and the vaccine coming out, but this is going to be in our future, it sounds like. So again, thank you both very much. To our BSA group, I just wanted to let you know that next year we're going to be kicking off the year with some virtual tours of schools, and certainly all the IES folks, if you would like to join us, that would be awesome too. And I hope you all have a happy holiday.
Great. Thank you so much. It's a pleasure.
Thank you, everybody.